All right, trying a new setup, trying a new layout, so bear with me. In this problem, we have R134A, which enters a condenser at steady state at 9 bar, 50 degrees C, and it goes through a 2.5 centimeter pipe. At the exit, the pressure is 9 bar, the temperature is 30 degrees C, and the velocity is 2.5 meters per second. We're told that the mass flow rate of the entering refrigerant is 6 kilograms per minute, and we want to determine the velocity of the inlet in meters per second and the diameter of the pipe at the exit in centimeters. So let's look at this problem a little bit. Let's set this up. So I'm going to have some fluid that comes through an entrance and goes into this control volume, which is a condenser. So it's going to look maybe something like this. And my fluid flow is going to be going like this. I'm going to call everything at my entrance state 1, everything at my exit state 2. So this is my exit, this is my entrance, or my inlet. And let's define what my control volume is. So I just want to say that this is my control volume. Okay, now I also want to just sort of go through the problem and write down all my information. So at P1 is going to be equal to 9 bar. Then T1 is equal to 50 degrees C. And at the exit, P2 is equal to 9 bar. And T2 is equal to 30 degrees C. We're also told that velocity, so V2, is equal to 2.5 meters per second, and the mass flow rate of the entering refrigerant is 6 kilograms per minute. So my mass flow rate of 1 is 6 kilograms per minute. Okay, we want to determine the velocity of the inlet in meters per second. Now, we're given a mass flow rate, and we know that for a mass flow rate, my mass flow rate of something, and we'll just say 1, is going to be equal to A1 V1 over this specific volume 1. This V is my velocity. This V is my specific volume. Now, these are pipes, and so the area of a pipe is going to be equal to pi d squared over 4. Well, we know, I didn't write this down, but we know that this diameter is 2.5 centimeters, or 0.025 meters. We're looking for my velocity, we have my mass flow rate, and we just need to figure out my specific volume. So let's solve this for my velocity. So V1 is going to be equal to m.1 V1 over A1. And let's figure out what V1 is equal to. So at the entrance, we're at 9 bar, 50 degrees C. We need to go to our table, and we need to look at 9 bar, which is over here. We need to look at this saturated temperature. My saturated temperature at 9 bar is equal to 35.53 degrees C. Now, 34.53 degrees C is going to be less than my operating temperature. So since T, which is 50, is greater than T sat, I know that I need to use the superheated table. Okay, so I go to the superheated table. I look at 9 bar. And then I go down to 50 degrees C. And I get that specific volume. Notice that it is not times 10 to the minus third. 10 to the minus 3. Okay, so let's go back to let's go back to here and let's write down everything we have. So I know that this is going to be 6 kilograms per minute. I want this in seconds. So I need to multiply this. 1 minute is 60 seconds. Okay, V1 is going to be that what we just found. So 0.02472 meters cubed per kilogram. And I want to divide by A1. A1 is going to be pi d squared. So 0.025 meters squared over 4. And I can bring a calculator up and just calculate that. So 6 divided by 60 times 0.02472 divided by pi Okay, so I get a velocity v1 is equal to 5.04 meters per second. Okay, so that's part A. Now let's look at part B. And in part B, we're asked to figure out the diameter of the pipe at the exit. Well, we're not given any information in the problem description about the mass flow rate at the exit, so I can't right away use this equation. So we need to look at our mass rate balance. This says that the change of my mass in my control volume with respect to time is going to be equal to the sum of my mass flow rate that's entering minus the sum of all my mass flow rates that are leaving. Now, we're told that we are operating at steady state, and this is an important assumption because our change in mass will go to 0 from steady state. What does this actually mean? Well, this means that when we're operating at steady state, we're assuming that we have our control volume is full of mass. As mass comes in, mass leaves, and there is no change in mass. Whatever's coming in is leaving. Okay. Well, this assumption would not be valid, say, on startup. At startup, if there's nothing in our control volume, then when we start it up, our mass is starting to fill up our control volume. After some amount of time, we will reach steady state, and then the steady state assumption would be valid. Okay, so because that's equal to 0, I'm going to get 0 is equal to, well, we only have one inlet and one outlet. So mi, my mass flow rate coming in, minus the mass flow rate that's leaving. So with a single inlet, single outlet, we'll get that our inlet mass flow rate is equal to our outlet mass flow rate. And in this case, this is 6 kilograms per minute. Okay, so let's use this equation again. M dot 2 is equal to A2 V2 over our specific volume 2. Well, we're going to be looking for our diameter. We're given our mass flow rate. Well, we found our mass flow rate. We're given a velocity. Now we just need to figure out what our specific volume is. So we're going to do the same thing, except now we're at 30 degrees C. So if we go to my table at 30 with 30 degrees C, well, now my temperature is less than my saturation temperature. that means I'm in the compressed region. Let me move this calculator out of the way. So I'm in the compressed region. Well, what the compressed region says, I don't have a compressed table for R134A. So it tells me that I do have an approximation that my volume at some temperature is going to be approximately equal to the saturated fluid at that temperature. So in my case, in our case, this temperature is 30 degrees C. So we need to use the temperature table. We need to look up 30 degrees C, and we can get this value. And just remember, in this table, we're times 10 to the third. Okay, so now we know what V2 is equal to. We know that V2 is equal to 0.8417 times 10 to the minus 3. So let's solve this for D. Let's do one step first. So this is M2, and this is going to be pi D squared over 4 times V2 over V2. We can solve for D squared, so we'll get D will be equal to M dot 2 V2 divided by velocity 2, then 4 comes up here, and pi goes down below, and we have a square root. So this is going to be equal to 4 times m dot, so 6 kilograms per minute. Let's deal with those units. So again, we're going to have 1 minute over 60 seconds. And then we're going to multiply this by V2, which we just found. 0.8417 times 10 to the minus third. And this is meters cubed per kilogram. All right, we divide by pi, and we divide by my velocity, which is 2.5 meters per second. And then we take the square root. Let's put that in the calculator. All right, 4 times 6 divided by 60 times 0.8417 e to the minus 3 divided by pi times 2.5. We take the square root. Of my answer. And we get that my diameter, I'm going to put it right here. So D is equal to 0.0065, and we're in meters. We can check that. So kilogram cancels with kilograms, minute cancels with minutes. The second is going to cancel. One of these meters is going to cancel with this, so we get meter squared. The square root will cancel out the other square over here. So we are good with our units. We're in meters. It was asking for this in centimeters. So this is going to be equal to 0.65 centimeters.